think of anything else for us. Temperature versus heat. Not the same thing. I measured up for today. Burnt my Hawaiian pizza. Should have used a Aloha temperature. Took a while for some of my therapy to really get that. Just dating today. Alright, I'm going to be here for a little while. There's a lot going on this slide. And all of it's important. I'll get you a head start though. I'll do attendance. Johnny's Kate, alright?
I don't know.
Okay. Fred's not here today. You want to check on him?
No, I didn't.
Oh, man. Alright, let's talk about heat and temperature. Temperature and heat are not the same thing. If I have my house, now let's do a house, let's do a campfire. If I have a campfire going on in my backyard, which is burning wood, and I've got a match, can we both agree that my match and my campfire both are burning wood? Follow me there? Both of them will burn at the same temperature or really close to the same temperature, but they won't have the same amount of heat. Temperature is a measurement of that property. So something can burn at 500 degrees Celsius, small amount or huge amount. It's an intrinsic property. When things are at room temperature, everything's the same temperature. But we're going to talk about, well then why does, if I take my hand and put it on the table, why does it feel cold then if it's actually the same temperature? Or why most people, I mean imagine this, unless you got super awesome special cars. Most cars you get into in the middle of summer, you get into the seat's like a little warm, but then that seatbelt buckle, screaming hot, burns you. But they're the same temperature, Evan. They're the same temperature, but they have different amounts of heat. Okay? Or more specifically, how does that heat flow transfer? Yeah, Alex?
Is it because one's a conductor and one's an insulator?
Kind of. It does have a little bit to do with that, but it's more of how much do they want to retain heat.
Sometimes I get in the car and I feel like the seats are
Yeah.
buckle.
That has to do with this thing called heat capacity, or its capacity to retain heat. Water has a huge heat capacity, which is why if you have a pool at your house, you go to a pool, why does the pool still feel warm even though it's nighttime and it's colder outside? That's because your pool retains that heat really, really well. The only thing we're focusing on is what is heat, what is heat flow, and how does it do with chemistry. So we're actually completely done with gases until the final. Never see gases again. We're now looking at a branch called thermochemistry, which is literally the heat chemistry. Brian, you right, man? You sure? You look down. Down. Now, just for my sake, so I know where you're at, in middle school or maybe ninth grade, at some point you talked about energy. What do you know? Just what do you know about energy, Lily?
It can't be created.
Or destroyed?
Yeah, it won't do it.
You know that's actually wrong. Your middle school teachers lied to you. But it's like,
She taught us about rocks. So.
but it's like big brain math of explaining why energy can't be created or destroyed. Also gets to Einstein's theory of relativity and equals mc squared. But like for the most part, energy can't be created or destroyed. But we found out after a while, like actually it can, and that's where it gets in a little bit of quantum physics and like time travel and all that stuff.
You travel.
Okay. So let's just go with the basis though that energy can't be created or destroyed, just because it makes our life easier. What do we measure heat energy in? Or just energy in general in? What do you got for me, Evan?
Degrees?
That's temperature.
Okay.
Energy. Do the terms potential and mechanical energy and kinetic energy ring a bell?
Mm-hmm.
Okay.
That was 6th grade.
Morgan took ICP. What is energy measured in?
I don't know.
Hudson, what you got for me?
Isn't that like newtons?
That's force, which force can be used to figure out work, which is a type of energy transfer. You guys in the right ballpark. That's power, which is how quickly you use the energy.
Oh,
We're like dancing around it.
I heard somewhere.
Ohms deals with electricity and resistance. Like if I had like a list of all the physics definitions of like basic stuff, you guys have hit every single one around energy. I'm just curious on what you guys know about energy, what you don't know about energy. Lauren, what do you remember about energy?
Not a lot.
Okay, and that's totally fine. I just don't want to be like up here, and you guys, I'm expecting you guys up here, and you're actually like right here, not quite there. Do you remember what energy is measured in? Does potential and kinetic energy make sense? Are those like ring the bell a little bit? Okay. All right. We are not going to be looking at potential or kinetic energy. That is a type of energy called mechanical energy. We're only going to be looking at thermal energy or thermochemistry. Because of that, we get to ignore a whole lot of slew of things and make our math actually a whole lot easier. Our math's going to be pretty algebra heavy-ish, but it can get crazier. Okay. So, how does heat flow? One of 3 ways: convection, conduction, or radiation. Just really simple. Convection is when hot stuff moves to cold stuff. Right? Majority of weather fronts are because hot air is moving to cold air. So when you open up the front door and your mom or dad yells at you saying you're letting the cold in, they're actually wrong. You're letting the heat out. So if you are wearing a jacket and you go outside in the middle of winter, you're getting cold. You're not actually getting cold. Technically, your tiny body is trying to heat up the world. And that's some really sad way of putting it. So you actually can't get cold. You can actually just get less hot. That's your convection. Conduction is actually you have to touch it, where Alex is kind of hitting on with conductors. Okay. Heat energy can go through stuff, but it has to be touching. Which is why you don't use a metal spoon when you're cooking, because that heat will go through the metal spoon a lot more quickly than it would a wooden spoon, because it's through conduction. The cool one is radiation, and that's when most people have seen it. You've seen a campfire. Campfire is glowing nice and bright. That is a type of thermal energy called radiation. Heat vision goggles work off of thermal imaging, all that good stuff. But when we transfer heat energy, what does it do? And we get to this word called enthalpy, which is a brand new word. Be careful on Googling enthalpy. You will go down a rabbit hole of deep, dark chemistry understandings. I'm saying I am talking about enthalpy in the smallest, most simplest of terms. We're just going to do that. Okay. Enthalpy is a measurement of energy transfer. So, hopefully, unless you guys are a little weird, you guys don't know how much money's in my bank account. But we could infer that I'd have at least $20 if I go pay for McDonald's food and I spend $20. You guys could infer that I have at least $20, right? We could also basically make the assumption I have enough money to pay for my car, for food, for house, and all this other stuff. Because my life isn't like falling apart in shambles, right? You can tell I have enough money. You really don't know how much though. Enthalpy is the same way. You know there's energy in there. We don't quite know how to figure out how much specifically. Einstein was really close with that equals mc squared stuff. But we can record in what energy is lost or what energy is gained. So what does this do for us? All right. If I have one water molecule, let's do H2O, and I were to break this up into oxygen and hydrogen molecules. Okay. Now I'm not looking at, it's not a balanced chemical reaction or anything, but I want to look at what is it we're actually doing. Well, in here I have two oxygen hydrogen bonds. Over here I have one oxygen to oxygen bond and one hydrogen to hydrogen bond. Now, just to give you just rough numbers, let's say that these two bonds had 200 joules of energy. Let's say oxygen had 50 joules and hydrogen had 25 joules of energy. Now, Brian already helped me out with it. Energy cannot be created or stored. We're going to say that for this class. It's not actually true. It takes 200 joules of energy to break that bond. Now, these are just fake numbers, okay? I don't know these numbers off the top of my head. I reference them off the table. So, 200 joules to break that bond. When that new bond is formed, I've only accounted for 75 joules. So, by looking at the difference here, where'd my 125 joules go? Right, and that's all thermochemistry is either heat is going to be gained or heat is going to be lost. So where does energy come from? Chemical bonds, thermal energy, moving particles, that's heat. And you can release or absorb energy. That's more next week's stuff. We're just going to look at heat and unpack it. So, don't really necessarily worry about this picture too much. All right. But I do want you to understand these two words. These are really important words. Okay. If I mix two chemicals together, it blows up in my face, there is a huge release of energy. That is called an exothermic reaction. Exo meaning to go outside or to leave. Thermic meaning heat. So literally heat leaves the environment, or specifically heat energy. So if you have a bomb on your hands, bomb blows up, all those energy that's stored in those chemical bonds breaks, releases heat energy into your face. What if you go the other way with it though? What if I do a chemical reaction that actually stores energy? Because at some point you got to make the compounds to make a bomb, right? So how do we get into that high energy state? Well, we take elements or atoms, we break them apart, we form new bonds. Those new bonds are higher energy, so energy was absorbed. You guys see this on heat packs, right? So you have those little hand warmers. Break it up and crack it open. What happens? Well, there's heat energy stored in those bonds, and when you crack open that, the iron oxide starts the chemical reaction, releases heat energy. Cold packs do the same thing. Break open a cold pack, but instead of being exothermic, it's endothermic. So that's why the cold pack gets cold. It's because the chemical compound it's making is absorbing the energy or absorbing the heat. So, let's look at this. Delta H is enthalpy change. So, if my enthalpy change, which is my energy, is positive, okay, you're usually doing something of going from a low energy state to a high energy state. So I got water right here. Hopefully everybody knows you go and start boiling water. It goes in from a low energy state to a high energy state. I haven't really changed the molecules, I haven't broken bonds. So how do we do that? Well, we take these atoms, we get them to move faster and faster and faster and faster and faster. And so at some point, these molecules stop from going from solids, they more now go to liquids, and then they go to the gas state. If enthalpy is decreasing, or it is less than zero, you go from a high energy state to a low energy state. For this class, what we're going to call is enthalpy change, at least for right now. We're going to use the same thing as heat for right now. We're going to introduce something a little bit different. Because there's also heat, there's also bond formation, there's also another thing which all goes into play, but we're going to keep it just as heat for today. How do we calculate heat? I'm going to tweak this though, because that's not my poster. My poster on the wall says MC delta T, and I'm going to stick with that one. All right, red poster on the wall. Only thing really new, well, I guess maybe not only thing, temperature, since we're no longer dealing with gases. Temperature is in degrees Celsius. We're going to only deal with Kelvin if you deal with gases. Mass is in grams. I'll skip specific heat for now. And then heat is in joules. Not joules as in what you hit. Alright. I'll be smoking joules in this class. Joules. Joules. The only thing we have to look at is this new letter now, C. Well, energy might be new to you. C is specific heat. If you have a high specific heat, right, that means it retains energy really well. That's back to that water. We're in a space here. If your heat capacity is really low, that means it loses energy really easily, really quickly. So why does your seat in a car, why does the seat not burn you, but the seat belt does? Well, that's because whatever the seat's made out of has a high capacity. It can store a lot of heat energy. It doesn't get rid of it really quickly. But that piece of steel, when you touch it, that heat transfers really quickly, and you can get some like third-degree burns or first-degree burns if it's hot enough. Reminds me of those kid slides, those all metal ones. Do those still exist?
Yes.
Well, like the cliffs of death, right? If the burn on the way down doesn't kill you, it's the sudden drop off at the end that will.
Yeah.
Okay. So why is that thing such a scorcher? That's because it's metal. When you're sliding down it, you're picking up all that heat energy that's stored into it, and you can get some first-degree burns pretty easily. Which is why I believe some slides are no longer be made out of metal, usually plastic now. I don't know. It's been a hot second since I played at the playground, Morgan.
That it hurt. The plastic ones still hurt.
Yeah. And then the ones at McDonald play place, shock you all the way down.
Oh
Yeah.
But isn't that because of like the metal screws inside?
Well, that's because you're sliding on an insulator. So rather than sliding on a conductor like metal, you're sliding on an insulator and you're picking up electrons along the way. So that's what static electricity is. Take physics, I'll teach you. We do a whole lab where we shock each other. Although I don't know, you got braces. I don't know if it'll make your teeth zing or not.
No, it doesn't.
We'll do it for science.
My braces will be off
Okay.
for next year.
Guess we gotta do it soon. Alright, that's it. Usually when it comes to this stuff, it's all gonna be just plug and chug, at least for now. So, let's just try this first one. Okay. Calculate the temperature change that results from a hunk of aluminum going from 2,150 joules. Alright, you have a 45 gram sample. Your heat capacity is 0.895. So all it is just plug and chug in the formula. So we got Q equals MC delta T. Our heat change is 2,150 joules. Mass is going to be 45 grams. My heat capacity is 0.895. joules per gram degree Celsius. What the heck does that even mean? And then delta T. Okay. I wrote those units in there specifically because watch. Do we see I have joules on the left side, joules on the right side? Those units will cancel out. I got grams on bottom. I got grams over here. And I'm just left with degrees Celsius. That's it. We're done. All I gotta do is plug and chug in a calculator. So before I do that, I have a thought experiment for the day. Are you ready?
Sure.
If I add 2,000 joules of energy, would you expect it to get warmer or colder?
Warmer.
Would you expect it to get warmer? The temperature would go up, right? That's it, okay? So, delta T comes out to be, I had the number off the top of my head. I don't have it anymore. It's a decimal. 2,150 divided by 45 divided by 0.895. I get 53.38 degrees Celsius. So let's ask a really silly question. This is like a pitfall for students. Is change in temperature the same thing as final temperature? No. Okay. Well, that's obvious now that I bring it up to mind. So, if we were looking for final temperature, you'd usually be given an initial temperature, and then you would do the last step. Because remember, delta anything is always final minus initial. What you got for me, Brian?
Couldn't we just multiply 45 times 0.895 and then divide it by 2?
Absolutely. Both math routes will get you there.
Alright.
But the way I did it in my calculator today was just, it prevented me from having to, I could do it in one get go on the calculator. That's just what I'm comfortable to. 53.38 degrees Celsius. Alright. So it's your change in temperature, not your final temperature. Alright, so next thought experiment. Morgan, you ready? I'm not even standing near the board, so you know I'm not even going to write anything down. Okay. What if instead of gaining 2,000 joules of energy, I were to lose it? What would you expect? The temperature would go down. Absolutely. Okay? So the only thing you need to be aware of is what direction is that heat going? Because if it says the temperature results in 2,000 joules of energy being applied, we know that energy is going into it. What if I said energy being taken away? How would you write that? Negative 2,150, and then the rest is the same. Okay, so instead of the temperature going up, temperature is going to go down. Why is it negative and why is it positive? Well, here's what scientists have done. Imagine in this box, the box on the left, okay, we're going to put heat into the system. We're going to call that positive. If heat is coming out of the system, we're going to call that negative. So here's your little, where things start to get in the realm of trippy. In order for heat to, on this left side, in order for heat to go into the system, that means the outside environment has to get colder or lower temperature. Same thing here. If heat is leaving the inside system, that means the outside system has to get warmer. So when you put your hand on a super hot seatbelt, you'd like sort of touch the one on the right. You put your hand on it, heat is now leaving this piece of metal on the inside, which is what causes your hand to get warmer. The other way, if you look at water, stick your hand in a pool, right, on a warm summer day. Stick your hand in a pool. Why does it feel cold to you? Here's the blue part. That's because the heat is leaving your hand and going into the pool. Right? So frame of reference is actually a pretty big thing when talking about heat and heat energy. So let's do that. Let's talk about heat and heat transfer with the experiment you're hopefully going to do tomorrow. I'm literally going to go to Walmart today and go pick up this class. Okay. Really cool part is we can do the whole thing with this setup called a calorimeter. I always have to focus on how I'm pronouncing it. Calorimetry is the science of measuring heat transfers or heat flows. So what you're going to do then is you're going to put a hot piece of metal, maybe. I haven't quite figured out what we're doing specifically. I got to find that out. Because if you have the chemicals do it, might do a chemical reaction. If not, we're going to put a hot piece of something in there. And then you can measure that heat flow. You could say as one thing gets warmer, the other thing is going to get colder, and we can look at the heat flow, and from there you can find some pretty interesting stuff. But how does it work? And that's the super important part right here. Q to A equals negative Q to B. What the heck does that even mean? That means the heat coming from A is going to be equal to but opposite to the heat leaving from B. Because energy can't be created or stored, at least not in this class. So we have to account for that energy transfer coming from somewhere. Another probably important thing, this number right here, heat capacity of water, you're probably going to use it a lot. 4.184. We're going to try this out. I have not done this lab in a hot second, no pun intended. So we're going to see if it works. Not quite sure what the equipment we have or what we got going on. All I know is we're going to swing for the fences because last week when we tried to swing for the fences for electrolysis water, it turned out pretty well. So what is the whole setup? I wouldn't necessarily worry about drawing this picture right now. We use styrofoam cups because they're wonderful insulators. Heat doesn't really come out, doesn't really go into. You use a double-walled insulation, so you use 2 cups stacked in there. On the top cup, you put a lid. That way we can say, and making the assumption, no heat is leaving or entering our cup system. We can then say is whatever is going to be the hot object or causing the reaction. So the reaction mixture right here. So say if you mix 2 chemicals in there, or at least a powder and a solution, mix them, and it's exothermic. Means it is going to release heat energy, and that heat energy is going to go somewhere, and it's going to go into the water. Well, what we'd then be able to do is say, well, I know the mass of the object I put in there. I know the temperature increase or decrease of these objects, so we can find heat capacities relative to one another. So let's do it. This question looks ugly, but it's really not that bad. All we gotta do is plug and chug, call it done, and we're done for today. Sample of copper is dropped It's at a temperature 175, dropped into a 150 grain sample of water. It raises the temperature from 24 to 41.5. What is the mass of the sample copper? I'm like, well, couldn't we just take this out and put it on a balance? Sure. But what if we're looking for heat capacity or something else? Okay. What I can say is that the heat that is coming out of one thing is going to be equal and opposite of the heat going into another thing. So all I'm going to do is, instead of putting A and B, I'm going to put water and copper. So the heat that is leaving from the copper, actually I'm going to do that. I'm going to do not what I wanted. I'm just going to start over again. Let's try it again. That the heat going to the water is going to be equal and opposite to the heat leaving the copper. As we did Q equals MC delta T. And that's all for the water. Q equals negative MC delta T. And that is for the copper. That's all it is. Mass of the water is 150 grams. Constant for water is 4.184, right? Yeah. The change in temperature, ooh, I don't have that. But how did I find that, Evan? What does the delta always mean?
Initial temperature, no. Final temperature minus initial temperature.
Final temperature minus initial temperature. So that's going to be 41.5 minus 24 equals negative, what's my mass of the copper? That's what we're looking for, right? Mass of the copper. Heat constant of the copper is 0.377. Hold the phone. I don't know my change in temperature of the copper. Or do I? Close. You're right. Let's just tweak that. Can we agree that my initial temperature of the copper is 175, right? So it's going to be minus 175.
Oh, is it good?
What's the final temperature going to be?
Well, if the other one went down by 24, wouldn't it be added 24?
Not quite, but you're on the right track though. They're not going to meet. Their differences in temperatures aren't going to be the same, but their final temperature is the same. So this one went to 41.5. 41.5. Follow me there, Alex? You take something hot, put it in a cold glass, anything, it's going to keep going until they're the same temperature. That's all it is now, it's just a math problem. Alright, somebody double check me on my math, make sure I'm doing alright. 41.5 minus 24.
17.5.
Sounds right. Times 150 times 4.184. I got 10,983. Anybody's welcome to contest it. 41.5 minus 175 times 0.377. I get negative 50.33 mass of the copper. Oh, never mind, this will be positive now because there's negative up front. So I got 10,983 divided by 50.33. Mass of the copper comes out to be 218.1 0.2 grams. As far as this week goes, that's going to be the ugliest the problem gets. It will not get uglier than that. Just the question type will change. You know, the words will change, but the most you're ever going to have to do is something that looks like this. Take the heat leaving, the heat gaining, break it to its components, plug and chug, algebra, on your way home. Okay? Alright. Here's what I do have for you.